Stephen,
Yes.
I'm already finished the survey.
Good, thank you. Yeah. You got internet? Yep. If you can you see that okay? If you look at page 43, it's a mechanics question. So it starts off. With a car of mass 650 and a driver of mass 70. So in total, what's the mass of the car and the driver? It's 720, isn't it? Alright, anyways, that's not even the first part. The first part is, what's Newton's third law? Yeah. For every action, there is an equal but opposite reaction. Okay. Part 2 is they want the weight of the car. So what's the formula for weight? Yeah, so it's just this, multiply this. What's wrong?
It should be 5 marks.
It should only really be 1 mark. 7063.2 newtons. Assume the weight of the car and driver is evenly distributed among the normal reaction force exerted by the ground on each tyre. Determine the... Yeah, so if you look here, what they're saying is, now this is really, it's only 1 mark, it's shockingly easy. If you look here, they're saying that the weight is spread over 4 tyres. So they want to know what is the reaction at each tyre. Yeah, divide by 4 just. So for the reaction at a tyre, oh wait, no, don't spell it the American way, T-Y-R-E, is 1765.8 newtons. So, how many marks for that now?
4.
Yeah, that's okay. 4 marks here for that. Okay, can I go to the B part now? Yep. So, when starting from rest, the car has an acceleration of 3.5. What is the driving force? Okay, so they want the... No, this again is actually very easy. They want the force. What is the formula for force? MA. And what's the M? 720, isn't it? Yes, that's okay. And what's the A? It's 3.5. So, that is 2625 newtons. Do any of you guys drive? Yeah, what do you drive? I mean, you drive back in China?
Yeah.
Or here?
No.
Can you drive?
But I can drive.
What type of car have you driven? Big car? Small car?
It's not too small. It can 7 people.
Oh, people carrier.
Yeah.
People carrier, yeah. And what about you? Hey, you go, come on, hurry up. What about you?
Yeah, I only drive driving free.
That's okay.
Yeah.
Small car? And you? Alright, what type of car? Okay. So, you probably know this, but with most small or medium cars, the engine is only connected to the front wheels or the back wheels, but not both. So this 2625, they say in the question, is coming from the front wheels. not all the wheels. So how much is it for just one of the wheels in the front? Well, that's 2625 divided by 2. But there are some cars that have the engine connected to all 4 wheels. Do you know what these types are called?
Yes.
Yeah?
Jeep races.
4-wheel drive, yeah. Do we know any examples? The Jeep, Range Rover, yeah. They're usually Jeeps, aren't they? Yeah. So anyways, with this car, the engine is providing, the force is provided by the front wheels. So that's why we only divide by 2, we don't divide by 4, okay? But that's not what they want fully. What they want is the total reaction, I believe. Yeah, total reaction they ask for in the question. Do you see that? In the middle of the question, what is the total reaction? Okay, so if I scroll down, there is one force going down. I think this is the answer for part A3. There's the weight of the car going down. How much was that, A3? 1765.8. No. Oh yeah, 176, yeah. 1765.8. Yeah? That's the weight going down. And we said in part 3 there's an upward reaction, and it must be the same. 1765.8. But now the car is moving forward. You know what, I'll just redraw these arrows a little bit more accurate. The reaction is actually between, here, let me put some grass on the ground here. There's the ground. The reaction is actually right here at the base. What did I say, 1765.8 newtons. And then there's a downward weight here of 1765.8 newtons. But now we have this extra force, the force that makes the car go forward. Where on the wheel should I draw this? Where should I put this force that makes the car go forward? Where should I draw that on the wheel, do you think? Yeah. Down and right, like here? Here to here, yeah? Or here to here?
I think it's center.
You think it's center? I think it's you said too, was it Hugo? Where did you think we should draw it? Was it center?
Yeah.
Yeah. What do you think? Center, bottom, top? Oh, okay, like this? Something like this? Now what about you, Who? Oh, you're all wrong. It's actually on the ground. Should have stuck with it. But why is it on the ground? Well, if you think about it, it's because the reason that the wheel moves is when the tyre rubs against the ground. Like, I don't really have anything that's circular, do I? Well, I suppose the lid. Yeah, actually, we use the whole bottle. Yeah. So, you know, when two things move together, you get friction. Yeah. So if I move my hand this way, the friction is going backwards. You know, if I move my hand this way, the friction is going backwards. So if you look carefully here, when the wheel is turning, okay, hey, focus there. Oh, right. When the wheel is turning, if you look here, which way is the wheel moving on the ground? Is it moving this way or is it moving that way? First or second? So here's turning, okay? So is it going this way?
Yes.
Or is it going this way? It's going this way, yeah. So if the wheel is turning this way, which way is the friction?
Opposite.
Yeah, so this is why the car goes forward. Okay? So, we should draw the force on the ground between the wheel and the road. Okay? How big is this force?
1, 3, 1, 2, 4.
Say that again, sorry. 1, 3, 1, 2.5. Okay, this is a reaction force technically. It's a friction force though, and this here is a reaction force, and this one here is a weight.
How to calculate the reflection? 1312.
It was this number divided by 2. So what they want you to do in this part of the question is add these two together. Okay? Can I go down? Well, in a minute. Yeah. I can go down now?
Yeah.
Yeah. So, what we have a triangle. The force to the right is 1312.5, and the force going up is 1765.8. And they would like you to work out the magnitude and the direction. So we can use Pythagoras. The magnitude is square root 1312.5 squared plus 1765.8 squared. Square root 1312.5 squared plus 1765.8 squared. Oops. So that is 2,200 newtons. And then the angle, who remembers the angle formula? Tan inverse 1765.8 over 1312.5. Oops, now I'm in radian mode, which we probably don't really want. So this comes in at 53.4 degrees. Right, so we got for this question 6 marks. Does it say? I better say some. Well, 53.4 above the ground, or with respect to the ground, we'll say. With respect to the ground. It's measured up from the ground. Okay, can we do the C part now? Yep. So, in part C, what happens is the car continues, but it reaches a maximum speed of 28. So, the force, what was the driving force of the car? It was 2625. So here your car has a force of 2625 newtons, and a force means there's an acceleration, and acceleration means the car keeps getting faster. However, the car's speed does not go past 28 meters per second. So what's the reason for this? Hey, I think you're in the wrong room there. Are you looking for Dennis? Let's go. What's the reason for the maximum speed? Any ideas? Why does the car not keep getting faster? Why does it reach a maximum speed?
reaction force.
Which reaction force?
Friction.
Which friction?
Air.
Yeah, so what's happening here is when the car gets faster, there's more and more air friction. And when the car is at this speed, the air friction is 2625 newtons also. The two cancel, and then Newton's first law says if there's no force, it will stay at a constant speed. So we need to explain this for for 1 mark. So as the car moves faster, the drag, this is called the drag force, the drag force will increase until it equals the drive force. And that Newton's first law then says it will travel at constant speed. Oh, sorry, I actually did part 2 here. This is part 2. Part 1 was they were just asking you for the name for this maximum velocity. So this is actually part 2 here, this answer. Part 1 is just the name. Does anybody know the name of this speed, which is the maximum speed it can travel at? Yeah, it's called the terminal velocity. Terminal velocity. There's only 1 mark for that. So far we have 4 marks. Hey, are you looking for Dennis? Dennis. Okay. You got that? Yeah. Okay. Nearly finished this question. The next part is, if I can go down, what is the work done? So who remembers the formula for work?
W equals P.
Equals what?
PT.
PT? Oh, that's for electricity. Oh no, that's not just for electricity. Yeah, you're right, that's right. But there's another formula too, but that's right. FD, yes, thank you. So work is force multiplied distance. The force is 2625, and in the question they say the distance is 8.4 kilometers. So this comes out as 22.05 megajoules. How big is mega? Power 6, yeah. That's part 3. I don't think this question has been too difficult. I know some parts might be difficult to understand, but the formulas have not been too difficult, right? Okay. If I go down to the last part now. So the last part is a bit about efficiency. So it says, the fuel of the car is 32 megajoules per litre. In your home country, you all use litres when you fill up your car, right? Yeah. So they're saying here that 1 litre of petrol has 32 megajoules of energy in it. Determine the rate of fuel consumption in litres per second of the car as it travels at a constant 28 meters per second if the total efficiency of the engine is 30%. So what they're saying is how much fuel is used per second if the car is 30% efficient. Okay. Right, so let me see. I think we may need to do, let's see, do we know the time? Yes, what we're really missing here, if I draw my picture for the car, which would be a great help, and we can work it out. How much work is done when the car has travelled 8.4 kilometres? What did we say? We had it there a moment ago, 22.05 megajoules. And we know the speed is 28 metres per second, but what we don't know is the time. But we can get the time as a distance over speed. So here the time is 8400 divided by 28. So that is 300 seconds. So you can say in 300 seconds, that means the car does 22.05 megajoules of work. So then in 1 second, how much work is being done? Well, that's 22.05 divided by 300. So that would be, if I write it out, car does 73500 joules of work. So in 1 second, the car does this much work. Okay. Now we also have our, what's the definition of power? Or what's the unit for power? Yeah, and what is that? What is 1 watt? Joules per second. So when I say the car does 73,000 joules of work in 1 second, that's the same as saying that the power of the car is 73,500 watts. Joules per second. Okay, now we can use the formula efficiency equals power out over power in times 100%. So here we have 30 equals. Now, what do you think? Is this the power out or the power in? Final answer? Which, out or in?
Oh.
Out. It's power out over power in times 100. Yeah? So 30 divided by 100 divided by 73500, flip that around. So then you get power in equals 245,000 watts. So this is how much power must go into the car from the fuel. And then this is how much power comes out of the car in the form of movement. That's nearly finished. We should now convert this back into joules per second. So this is 245,000 joules per second.
I have a question.
Yeah.
How do you calculate in 1 second?
I just took this number and divide by 300 because this number here is for 300 seconds.
Yes.
So this number here is for 1 second. So I divide this by 300. But don't forget, Louise, that this is mega, so it's a 10 to the 6.
Okay.
So it's 22.05 10 to the 6 divided by 300 is this number. Okay? Right. So, how much, I should write this back in megajoules, I think. So this is 0.245 megajoules per second. How many megajoules in 1 litre? It says it's 32. So think about this. If the car was like a really big truck or something, I don't know. If the car needed 32 megajoules per second, then how many litres would it need per second? 1. If the car was doing 64 megajoules per second, it would need 2 litres. And if the car was doing 16 megajoules per second, how many would it need? It need a half. So what would you need to do to this number to work out how many litres per second you would need? So 0.245, what should I do to this? Yeah, this is megajoules per second, and I should divide it by 32 megajoules per litre. So this is 7.66 milliliters per second. Because what happens here is you can see that the mega and mega cancels, the joule and the joule cancels, and this per litre can go up to the top as litre, so it's litres per second. But this number is really small. It's milli, 10 to the minus 3. So it's milliliters per second. So this car uses about 8 milliliters per second. 8 milliliters is not that big when you think about it. Like, how much maybe in that lid? Would that be 8 milliliters, Louise? Can I have the lid? Just the top. Just the top. Yeah, the lid on the top. Yeah, yeah. How big is this? Would this be 8 milliliters? No, that's more, isn't it? Maybe half of this? Or less? What do you think? 8 milliliters? Maybe half of this? So this car per second uses half of this. Maybe less even. Doesn't sound like a lot, does it? Here you go. The car, by the way, this number here, 30%. Where's it gone? That would be normal for cars. Cars are not very efficient. 30% would be normal. Okay. Maybe good cars could be 50%. 30% is normal. Anyway, that's the mechanics one done. So let's just